welcome everybody to Advanced Atomic and Molecular Physics. My name is Markus Koch. I'm Associate Professor at the Institute of Experimental Physics, and I have the great pleasure to give this lecture today. So Professor Hauser asked me to give this lecture because the topic we will talk about today is, there are actually two topics. So this will be laser cooling and ultra-fast laser physics. And these are two really, I would say, state-of-the-art techniques, experimental techniques, in both of which I have experience. And I guess this is the reason why I can introduce this to you. So first of all, let me ask you, can you hear me? Right, I'm using an iPad, and there's sometimes issues with volume intensity or volume control. Okay, perfect, thank you. And before we jump in, let me just start by sharing my screen. I have prepared two PowerPoint presentations for that. And I also asked Professor Hauser to forward the PDFs of those to you. So probably you have already received them. If not, I'm sure you will receive them very soon. Okay. So before we jump in, what I wanted to say is I want to ask you something. I would like to have as much discussion as possible. I mean, these two topics we're talking about today are really two, I mean, you can give a whole lecture on each of these topics. So I'm only scratching barely on the surface of what you can do. And the more important it is for you to take at least, or the take-home message for you should be that you have an idea, or at least a rough idea, what you can do, what are the main aims in each of the fields, and how these are kind of connected to your physics course. So if you have any questions, I will stop at some points and ask you questions or ask you about your opinion. So just please feel free to answer, and also ask anytime you want to. So let's have as much discussion as possible. Okay, let's go to the first topic, quantum optics laser cooling. But in a way, we are talking about two really extreme cases in physics. This is also connected to the WebEx name: very cold, very cold, and very fast. So short, high time resolution in ultra-fast laser physics, and now in quantum optics, very cold. But what is cold, and why would you want to go to very low temperature? So what's your idea? Can you give me some feedback? What are your experiences with quantum optics laser cooling? What have you heard about already? What do you expect?
Maybe you can reduce thermal noises that appear because of the temperature of certain particles.
Right. Okay. So thermal noise. Yeah, but probably let's explain first what is cold. So which temperatures are we talking about if we say ultra cold physics?
A few Kelvin.
Go again, sorry.
A few Kelvin.
A few Kelvin, that's much too hot. Still much too hot. Anybody? What do you think? So who is brave and can say a really low number?
A few millikelvin.
Millikelvin. Almost getting close on nanokelvin. So we're talking about 100 nanokelvin. So this is really about a millionth of a Kelvin below the absolute zero. Why do you want to explore physics at this range? Because what you mentioned before is you want to reduce noise and thermal like fluctuations or stuff like that. For this, few Kelvin to 1 Kelvin range would be sufficient. So depending on the application, 10 Kelvin or 1 Kelvin would be sufficient for that. But why do you want to still go like 9 orders of magnitude, or say 6, 7 orders of magnitude below that? What's the game? What do you want? What's the aim? What do you want to explore there? What's the new physics?
I mean, I don't really know about quantum optics, but at least from statistical physics, I know that if I go into low temperature, I go in the regime of more quantum effects than the classical ones.
Exactly, right track. You want to explore the quantum nature, quantum statistics, Bose-Einstein statistics, BEC, Bose-Einstein condensation. That's where we want to go to. Nobel Prize in physics I should know that, late 90s, 96, I think. Wolfgang Ketterle and co-workers. But so this is the aim, really. We want to go to a regime where matter behaves completely different. Particles in a gas moving so slowly that they're, they can be in quantum, they can be treated or are treated as a wave packet, and the extension of the wave packet is inversely proportional to the kinetic energy, basically to the momentum, yeah, and the wave packet becomes extended so much that wave packets of neighboring particles start to overlap, and you go into this, if you are working with bosons, you go into this ground state where all the bosons condensate in the ground state. You know that from quantum statistics, and this is exactly what people were after when developing these techniques. The question now is, how can you get that cold? I mean, a nanokel or 100 nanokelvins, even microkelvins, is really difficult to reach, and this is what we're going to talk about the next 15 minutes or so. Okay, so what is the basic principle? Very simple, photon absorption, right? So you have come across photon absorption. So photon, you take an atom, a resonant photon can be absorbed, and you get an excited atom. You always have, my suspicion is that you only looked at this process in terms of energy. So the photon energy has to equal the energy difference of two quantum states in the atom, the ground state excited state, electronically excited state, but you never really considered the momentum of the photon. Of course, a photon has a momentum, yeah, h bar k, and since the photon is annihilated in this absorption process, the momentum conservation has to be fulfilled, of course. So the atom, if you assume that this was standing still before the absorption process, it would be moving to the side afterwards. It would be moving with the same, or it is moving actually with the same momentum as the photon had before. Yeah, and so in other words, you have to watch the photon absorption and also the emission process in terms of energy conservation, which you did up to now, but also in terms of momentum conservation, as all processes in physics, so nothing new here. The important difference, though, is that the excitation process, if light is coming always, you always shine the laser light from the same side on the atoms. So the kick due to absorption is always from left to right here, for example. But the re-emission process on the right-hand side here is statistically averaged over in any direction. So after many excitation and re-emission processes, you gain there's a net momentum from left to right. Okay. Sorry, wrong direction. So yeah, I should have shown this before. Let's zoom in here a little bit. So you also can think about this. So no, let's say the next step is now we're not looking at atoms that are standing still, but atoms that are moving to the side from right to left. So the photons, sorry about that. The photon that's being absorbed is counter-propagating to the atoms. So this will, upon excitation, this will reduce the momentum of the moving atom, so it will slow down the atom. And since the re-emission, the spontaneous emission, is again spatially averaged, then this will lead to slowing down of the atoms. Okay, so nothing new really here. And the next step is now to watch at this in a way from the moving system. Up to now, we have been looking at this absorption emission processes from the lab, frame. We're now moving. We're now switching to the moving frame of the atom, das bewegte Bezugssystem. So if we have a counter-propagating, the atom's moving and the light counter-propagating, zoom in a little bit, the atom sees, due to the Doppler effect, sees blue shifted absorption frequency. So let's assume the transition actually requires a red photon on the red side of the visible range, for example. The atom counter-propagating to the laser beam will, due to Doppler shift, see higher photon energy, a green photon, for example. Yeah, so this is indicated here. So Doppler shift is an important contribution. So this is kind of the combination of step 1 and step 2. And since the re-emission is in the reference frame of the atom, so the photon energy that's being re-emitted has a higher photon energy, indicated as blue here, compared to the absorbed photon. Yeah, so this is now an energy picture of the before we looked at that in the kind of momentum picture or momentum conservation. Here this is pure energy treatment, if you wish, and in total the atom absorbs a red photons, so low energy photons, and re-emits higher energy photons. Yeah, because during the absorption process it's counter-propagating, and this also makes clear that the atom is actually losing energy. Okay, so after a certain excitation or a certain number of excitation emission processes. So let's put some numbers to this. So for example, so the first laser cooling, the first Bose-Einstein condensation, and even before that, the first laser cooling experiments were almost always done with sodium or alkali metal atoms, sodium, potassium primarily. And for potassium atoms, for example, natrium, you have a recoil velocity for one excitation re-emission process of about 3 centimeters per second. So this is after one excitation emission process, the velocity of the sodium atom. Depends a little bit on the amount of detuning and the initial velocity, but on average. Okay, so with a natural lifetime of about 1 to 10 nanoseconds, so the natural lifetime of sodium is a few nanoseconds in the single-digit nanosecond regime. So meaning you can easily drive about 10 to the 7, 10 to the 8 excitation spontaneous emission cycles, and this results to an acceleration, yeah, of about 10 to the 6, so 1 million meters per second squared. So 10 to the 5 times the G value, actually. Yeah, so the 10 to the 5 times the G value. So this is a huge deceleration. Okay, so much about this fundamental process, but how can you use this for laser cooling now? And the topic here really is Doppler cooling, because again you are making use of the Doppler effect, namely that the atom counter-propagating to the laser beam sees a higher photon energy, absorbs, and therefore kind of loses energy when after re-emitting the photon. Okay, so what we're looking here now is the velocity as function of the force. Sorry, other way around, the force as function of the velocity. So the force acting on this particle as function of the velocity, and obviously this depends on the detuning. So this curve has a maximum. So for a certain velocity counter-propagating to the laser beam, the force will be acting on the deceleration force acting on the particles will be a maximum, and for faster or slower atoms, the force is a little bit lower. So this shows already that for example, you start with an atom up here, so it can decelerate, it gets slower. But as it gets slower, it kind of falls out of resonance, because if it's lower, the Doppler shift results in the fact that the atom does not see the laser beam as resonant laser beam anymore, and the absorption probability decreases, and therefore the force decreases, because the number of excitation emission cycles decrease. Okay, so this is a velocity dependent force. Okay, and what's indicated here also, typically you're working with two counter propagating laser beams, because if you start off with an atom cloud, the atoms are moving in various directions, and you will have some atoms moving to the left, some to the right, so you can address both. And typically you even use 6 laser beams, so in all 3 directions. So 2 counter-propagating in X direction, 2 counter-propagating in Y, and 2 counter-propagating in Z direction. So no matter in which direction the atom, a certain atom moves, it always will feel kind of some force from any direction.
May I ask something about this?
Yeah,
already?
sure.
If I send it from both sides, don't I with one side also accelerate the atoms to apart? So in the case,
very good. Yeah, very good question. Answer is no, but
No.
thank you nevertheless for asking, because the laser is detuned to the red. So the photon energy is a little bit below the resonance frequency for absorption. Yeah, so it can only addresses counter-propagating atoms. So the atom has to be moving towards the laser beam in order to see slightly higher photon energy, in order to be able to absorb it. Yeah, if it's moving away, it sees the laser beam detuned to the red, so it's the initially too low photon energy becomes yet lower, and there's no probability for absorption. But everything really depends and stands and falls with the amount of detuning. Yeah, but we have to be careful here now. We have to distinguish between the fundamental process behind that. I just want to explain to you the fundamental ideas. Yeah, the realization is something completely different. So there are technical problems. You have multiple transitions and stuff like this, and dark states and lots of problems which you have to solve. But this is really the 1 or 2 underlying fundamental principles. Okay.
Can I also ask about the same thing?
Sure.
Can it also be a problem if you have atoms of a different kind? Because then maybe for this one atom you could tune it, and this redshifted Doppler broadening would be too low of an energy, but it might just correspond to one of the other type.
Yeah.
Or is that one of the difficulties you were talking about?
Yeah, also very good questions. So typically you're working in a magneto-optical trap. We're coming to this. So this is in ultra high vacuum, and you have you're working at a base pressure of 10 to the 10 millibar or so. So basically no particles anymore in the vacuum, and then you put into this vacuum chamber a certain amount of sodium atoms, for example. Yeah. So this kind of solves the problem to some extent, only because remember you have different isotopes of each element. So even if you have a conventional piece of sodium and you evaporate a little bit, you generate a sodium vapor, but you still have different isotopes, and there's an isotope shift. And what you mentioned is also true not only for different species, different elements, but also different isotopes. Okay, but this also falls into this regime technical problems. You have to solve them, and people are doing. I mean, believe me, I did two research stays in 2 groups. One in Innsbruck. So Innsbruck is a very famous group in the field of Bose-Einstein condensation, and also in Florence in Italy. And these are very, very complex experiments. Yeah, so you have for one experiment 2 full laser tables full of equipment and optics. And what people do, for example, is if they want to make molecules, they cool down atoms of sort A, for example, potassium, and atoms of sort B, for example, sodium, and then they want to form cold molecules. So you have not 6 but 12 laser beams, and things become very, very complicated then. Okay, but this is also related, so that the experiments, so the first BEC was in 1996 or so. So this is also explains why this has been realized relatively late in terms of. So it took a while to develop all this. Okay, but does this answer your question?
Yeah, thank you.
Okay, perfect. So important here is that this is really a velocity dependent force. Yeah. So there's no spatial dependence about that, and the atoms will become cold. Yeah, and the range or the limit, the so-called Doppler limit, the lowest temperature you can gain with the Doppler cooling technique, is about 100 microkelvin already. Yeah, so this is quite low. But the disadvantage is that the atoms will drift out of this interaction volume, because you cannot slow down them really to zero, but with this remaining velocity, they will just drift out of the volume. Okay, so let's see what you have to add in order to, or let me stay here and ask you, do you have any ideas how can you now add to this quite complicated setup already? How can you add a spatial dependence? What fundamental effects do you know already that might add spatial dependency? How can you make to absorb an atom in the center? Yeah, well, let me just quickly draw here. So let's assume we have 3 different laser beams here. So in X, Y, and Z direction. How can you achieve that an atom absorbs in the center differently from out of the center, for example? Any idea?
Changing the energy spacing?
Yeah.
Yeah,
yeah,
magnetic
that's
field,
the right
maybe, or something like
magnetic
that.
field, exactly. Okay. That's what I wanted to hear. Exactly, magnetic field. So you know about Zeeman energy level shift. Yeah. So in principle, you can take electric fields, static electric fields, or magnetic fields, and the energy levels will shift energetically. Zeeman splitting, for example. So MF states, so the total angular momentum quantum number MF, and the corresponding states, the state energy, is dependent on the magnetic field. So you have some expression like energy equals MF state times there's a H bar always, and B field, for example. Yeah. So Zeeman splitting, and that's the next kind of step of complexity, namely a magneto-optical trap. Yeah, or short MOT. This is MOT. This is really what enabled then this was the next important contribution towards Bose-Einstein condensation. And what you have here is you see, go back, you see 2 sketches here, so a 3D sketch kind of, and the 2D sketch here. And what you have are 2 coils in blue here, and these are so-called anti-Helmholtz coils. So the anti is important, and this means that the current flow direction is counter-propagating. Yeah, while it's clockwise in the first coil, it's counterclockwise in the other. It's indicated down there. So here, you're probably familiar with Helmholtz coils. In a Helmholtz coil, the current direction would be the same. So you have a kind of homogeneous magnetic field in the center. Here, with anti-Helmholtz configuration, you have approximately B0 in the center. And as you move out of the center in any direction, really in 3D, in any direction, the magnetic field increases. Yeah, this is indicated in a way by this magnetic field lines here. Okay. So you have a different Zeeman shift of a certain level concerning the transition you want to use in the center compared to out of the center. And in addition to that, you have these laser beams. So these are here, and typically you work with a single laser beam and a mirror M here. So you have a kind of a standing wave in the middle, so counter-propagating laser beams in all three directions. Yeah, and everything has to be in a vacuum chamber. Actually, under very, very high vacuum, 10 to the 10 millibar or so. Okay, sorry, direction. So we had this already, anti-Helmholtz coils, and we also talked about the Zeeman effect that allows you to spatially to obtain a spatially dependent energy shift. Yeah, so the force depends now on both on the velocity and on the kind of position within this 3D field configuration. And again, you have to work with the detuning such that typically the spatial force is 0 in the center and non-zero out of the center, and such that it's directed towards the center. So this allows you to obtain a cold atom cloud in the center of the mod. Okay, and this was, so the realization of that trapping of atoms and cooling of atoms was rewarded with a Nobel Prize in 1997 to these three gentlemen here. And well, you could, well, the temperature limit is still the same, 100 microkelvins for the magneto-optical trap. What we have added is so far is only the spatial dependency. But then since you have a small cloud, so like spatially confined amount of atoms, and we're talking about the couple of millions of atoms that are trapped in this cloud, you can switch off the cooling mechanism, yeah, by switching off the electric field or reducing, switching off the magnetic field or reducing the magnetic field. And what you can do then, relatively simple, is evaporative cooling, yeah, by reducing the magnetic field and changing the shift of the laser, the redshift of the laser frequency. You kind of, this is sometimes, if I draw the energy as a function of one coordinate, x, for example, you can say, okay, there is a certain, probably something like a local minimum, yeah? So there's a local minimum in the center, and this depends how deep or how shallow this minimum is, depends on the combination of the magnetic field and the laser frequency. So by changing the magnetic field, for example, you can reduce this barrier height, meaning that, for example, so within the cloud, you always have a kind of energy distribution, and with this evaporative cooling, you just boil off kind of the hot atoms of the cloud, and you can further cool this down and reach temperatures 3 orders of magnitude below that, roughly in the 100 nanokelvin regime. Okay. Let's see what you can do here. So let's start with the Doppler limit, 100 microkelvin. The velocity of a typical sodium or potassium atom is on the order of 0.1 meters per second. This is very slow already, but still too high. So you're still talking about classical particles. Why? Because the de Broglie wavelength is on the order or even smaller than the atom diameter. Yeah. So this is the high temperature regime, although 100 microkelvin is a low temperature already, but still in terms of a quantum gas, this is considered a high temperature. Yeah? If I then go further down, 100 nanokelvin, the Broglie wavelength increases the atom diameter, and the particles, let's zoom in here, the particles are not represented as points anymore, but the quantum nature comes to the front, and the Broglie wavelength kind of exceeds the particle diameter. Yeah, so you're really treating the particles as wave packets now. Yeah, and then there's a critical temperature depending on the material and particle density and some parameters, where when the wave functions start to overlap, okay, then the condensate into the ground state, for example. Yeah. So when this critical temperature is reached then when the de Broglie wavelength equalizes roughly the particle distance. Yeah. So when as it's indicated here, when kind of the distance, the distance of one particle to the other roughly is in the range of or equals the de Broglie wavelength of this wave packet. Yeah, then the matter waves start to overlap, and some particles, the colder ones of the ensemble, start to condensate. And if you go to zero, only at T equals 0, you have a pure Bose condensate, but typically you have a mixture of some hotter particles and condensed BEC particles. If you want to learn more about this, of course, I can recommend Wikipedia, but another webpage that is pretty nice is this one here from the Ketele group, Wolfgang Ketele, one of the Nobel Prize winners. 2001 was the Nobel Prize. I think 1996 was the first BEC realized, plus minus a year or so. And in 2001, Cornel Weyman and Wolfgang Ketele at MIT received the Nobel Prize, and Ketele is still working this regime, or has been a couple of years ago, and has a very nice homepage. Okay, so do you have questions to that? So this.
Actually, maybe so. When we say it combines to one common wave package, before we had low temperature, we say there is already this overlap in general, or is this just that so if we are above the critical temperature, we still do not have complete overlap between all these wave functions of the individual particles, but they are on the order of the distance. I don't really get the difference between these two, what the critical point here is.
Yeah, I think probably these 2 points here, step 2 and 3. So in step 2, the Broglie wavelength is the wave packet is already larger than the conventional particle diameter, so the atom diameter, if you consider the valence electron radius, for example. So this is already behaving as a wave packet. If you would make, for example, diffraction experiment with that, you would measure, or would be able to measure this extended wave packet. Okay, if you further cool it down, the wave packet starts to grow, so it becomes larger and larger because the momentum goes down. And I'm really not an expert here, but I think the requirement in order to have condensation is that the Broglie wavelength is roughly equal the distance. So if the wave packets start to overlap, they kind of there is a phase relation established between the wave packets of two individual particles, and this must contribute to the condensation into the ground state, really falling into the ground state of according to the Bose-Einstein statistics.
So in 2, we don't have the case the wavelength is equal to the distance between the particles.
Exactly. Yeah, I think here it's lower. In case 2, the wavelength is lower than the average particle distance, and in case 3, it's comparable or roughly equal.
But still, even though that the wavelength is shorter than the distance, we still have overlap between the individual wave packets, waves of the particles.
In 2, you mean, or in 3?
In 2.
2, yeah, definitely. And they are pretty sure there are all other quantum effects, so that take place already. So they wouldn't condensate into the ground state, but there must be some interaction between the particles that's recognizable in experiments. Don't know really now what this is, but so one thing is people do, Markus Arndt in Vienna, for example, does diffraction, so particle optics. So he's using large molecules, cooling them down and doing diffraction of gratings, for example. And he shows that they behave like waves. And but I'm not really aware of experiments now that show that there is an influence of the kind of overlapping of the wave packets here already. But it definitely behaves as a wave, and you could measure the wavelength in scattering or diffraction experiment, for example, as you do with light waves.
Okay, but only of the individual atom and not
Yeah,
yet combined, like in the case.
I would think so, yeah, because each particle, energy-wise, each particle has a different momentum, so a different energy. So if you picture these energy states, sorry, if you picture these different energy states, the two particles that undergo a collision, for example, might be at different energy levels, so there's not too much interaction. But probably if you do scattering experiments, if you measure the scattering cross-section, so one particle colliding with another, there must be a difference whether the wavelength, the de Broglie wavelength, is kind of long or very, very short. So I guess ultra cold scattering experiment should show an influence, because there might be an interaction between two particles if the de Broglie wavelengths overlap. Okay.
Yes.
Okay.
Really help.
Perfect. Thank you. So if you want to further do some research on that, look for ultra cold scattering or quantum scattering, for example. This will be. I'm sure one can find experiments, or write me an email if you wish. If you're interested, I'm sure I can find an experiment or a paper for you. Okay, I have to watch the time a little bit because so much interesting stuff to talk about. And are there any further questions? Sorry, I didn't want to interrupt. Are there any further questions to quantum?
Yes, I have a short question. So when you cool down the particles, how do you prevent that the thermal radiation from the chamber walls, since the chamber walls are not at the same temperature, interact with the particles and heat them up again?
Very good question. These are atoms and they don't absorb in the infrared. So chamber walls are room temperature. So you have wavelengths of several micrometers. And if these were molecules, you could they would interact with this radiation with vibrational energy. But these are atoms and they do not interact. So they simply cannot be excited at this wavelength range. So there's no interaction, no heating from the radiation, from the chamber walls. But a very good question.
Thank you, I see.
Further more questions? Okay. Then we shift gears and let's go to ultra-fast laser physics. So this really is my field of research. So that's the field I'm working in. My background to this is I did a postdoc stay at Stanford University in, it's long ago, 2012. And when I came back to TU Graz, I started with ultra-fast laser physics, ultra-fast time-resolved spectroscopy there. And coming back to TU Graz, I established the first ultra-fast laser lab here, which is in our basement. And this kind of has been my research field since then. What is fast? I asked you what is cold. Now you have to tell me what is fast. What's a short amount of time?
Femtoseconds?
You can femtoseconds, exactly. So I hope everybody is familiar with femto. So millimicron, nano, pico, femto, 10 to the minus 15 seconds. Kind of the regime. There are two regimes nowadays: the femtosecond regime and the attosecond regime. So in terms of temporal resolution, on the order of 10 attosecond is the shortest or the best time resolution you can achieve in physics. I will today mainly talk about femtosecond time resolution, which is basically the time regime of chemical reactions. So we can watch chemical reactions on their natural time scale. Okay. second question is, why do you want to have this time resolution? So what is, or if you want to put this question in a different manner, you're aware of CW spectroscopy. So typically laser spectroscopy, you try to learn about energy levels of atoms and molecules. And by knowing where these energy levels are, where the transitions are, you learn about properties of this. Yeah, this is all non-time resolved. Why is it important to be able to investigate processes with time resolution? Why do you want to watch chemistry with time resolution?
You just can investigate this black box of transitions and study the dynamical behavior of electron densities, which are especially of interest in chemistry.
Exactly, yeah. So you want to study the process that's going on, basically. And as a motivation, I like to show these pictures. So these are photographs with a lousy resolution, I admit. These are photographs of a cat. So you can see probably here, a cat is being held upside down. And you know probably if you hold a cat upside down and you just drop it in a way, it manages to turn around and land on its feet within half a meter or so, yeah, surprisingly less distance. So this is called the falling cat problem. These photographs are 100 and 30 years old almost, yeah, so pretty old. And these are among the first time resolved photographs, and the aim of this was to resolve a very important research question back then, namely how does the falling cat manage to land on its feet. Yeah, and this may sound funny now, but this was really an ongoing discussion where big names, big physicists contributed, like James Clerk Maxwell and this like. And it was simply just not known, because the problem was if you assume the cat as a rigid body, angular momentum conservation would not allow the cat to turn around. Yeah, so people did not know how to explain this. Yeah, and there were a lot of cats dropped. You can read the Wikipedia article. Lots of cats dropped out of the windows. A lot of cats died, unfortunately. But people really wanted to understand this, and the solution was achieved by these photographs. And as you can kind of see here, the cat first is kind of bent, and then it kind of rotates the front and the rear part first. So in a way, by bending over and rotating the rear and the front part individually, and this probably can be seen here, together the total rotation, angular momentum conservation is fulfilled, and physics is kind of conserved or safe. Okay, the point I want to make here is this was a huge problem, how a cat manages that, and this could only be solved by observing the process. Yeah, so it is insufficient to see the initial state and the final state. If you want to learn how the process works, you have to observe it on its original time scale. Now, nowadays, the systems are smaller. We're looking at molecules. So you probably, who recognizes this molecule on the right, on the left-hand side? I don't know if you want to call it a molecule. So what's that?
DNA.
A DNA strand, exactly. So a DNA consisting of these 4 nucleic bases, as you might know: thymine, adenine, cytosine, and guanine. This was some work I contributed to in Stanford. This is why I came into this nuclear-based research. And I mean, I think we all agree that the DNA really, and these nuclear-based molecules, they have a very, very important function in human life, if you wish. Yeah. But they also have a big problem. So here you see the wavelength, or the absorption cross-section, as a function of wavelength lambda. Okay, and you see that all 4 of them absorb rather strongly around 260 nanometers, so in the UV light. So whenever you go out into the sun, some sunlight shines on your skin, which is unfortunately not possible today, but in general, they become photoexcited. Yeah. So you might ask, okay, why is this a problem? The problem is that in the excited state, so this is a potential energy surface. So are you familiar with those potential energy surface diagrams, or is this something new? Can you give me some feedback?
Do not really completely recognize the one that we see right now.
Okay. Not this one in particular, but in general. So you have, as a function of a reaction coordinate, you have energy of electronic states. Yeah. So the reaction coordinate in this case can be a bending angle of the molecule or a distance, for example. For example, this can be a CH stretch distance, any one of the normal modes of the molecule. And the energy depends on the CH distance, for example, or on this one reaction coordinate. Yeah. And the thing is, if you photoexcite it from the ground state, so this would be the 260 nanometer excitation now. In the excited state, we call this a pi star state. This is molecular physics now, not so important, but in the excited states, it's a reactive molecule. Yeah, so it would undergo chemical reactions with the environment, and this, of course, would be very, very bad, because then the DNA strength would change, and unfortunately, sometimes this does happen, and this is the cause, can be the cause of cancer. Okay, but the big question was, given the strong absorption cross-section in the UV range, the DNA molecules, the nucleobases, become photoexcited many, many times, all the time, basically. But it's luckily very seldom that the damage of the DNA strand occurs. And the reason for that is obviously, so people knew right away that this photoexcited state must decay very quickly through a non-adiabatic relaxation to the ground state. Yeah. So in other words, this kind of dangerous potential energy, the photoexcited energy, is converted very quickly and very efficiently to heat. Yeah. If it goes back to the ground state, this you have a conversion of potential energy to vibrational energy. Yeah. The molecule gets heated up, and the heat is distributed over the DNA string, and everything is fine. Okay, it doesn't break apart. So dangerous, it's only in the excited state, yeah, in this pi star state. And it was kind of clear right away that the nucleobase molecules do that, like it was clear right away that the cat rotates around, but it was not understood how it does this. Yeah, so what's the reaction pathway of this? Yeah, and this has been an ongoing field of ongoing research. That there are still papers being written on that, and research done, and it's still not fully 100% clear for all the four nucleobase molecules, but in principle you can get an insight how this works. And you get this from so-called pump probe measurements. I will explain this a little bit closer later today. But we look at some observable, some signal. This is a photoelectron signal, for example, or an ion signal in this case. That's not important. We see that this signal that depends or corresponds to the excited state decays very, very quickly within less than 200 femtoseconds, and then yeah, well, there's other dynamics. So the interpretation of the signals is very complicated also, but from those experiments you get an idea with femtoseconds time delay on a femtosecond scale how this conversion of the excited to the lower state takes place. Yeah, so this is for me very similar to the CATS problem. It was known before the possibility to observe this that the cat rotates around, but we only learned how these molecules in this case do that by doing time resolved spectroscopy on them. Okay, so this is kind of motivation. Don't be frustrated or afraid if you don't understand. Again, I mean, you can give a whole lecture, a whole course, probably even 2 semesters on stuff like this. So I really want to give you an idea where this goes to. By the way, if you're interested in these topics, you can, of course, there's a lecture, 2 lectures that are connected to this field of research. So this is fundamental optics, which I'm giving in the winter semester, and ultrafast laser physics in the summer semester. Both are in the quantum optics molecular physics module and in the nano and laser optics module. Okay, so let's look into this time scale. You immediately said, okay, fast resolution, temporal resolution is femtoseconds. That's true, but how short is a femtosecond really? And I think you can realize this in 2 ways. First, by comparing it to length scales. We are somewhat more familiar to length scales. So if you start with the meter length scales, 15 orders of magnitude, a femtometer brings us down to the extension of a proton. Yeah, so we can look into a proton already and kind of on the scale of or dimension of the size of quarks. So in comparison, 1 second, the resolution or the limit for temporal measurement based on electronic techniques is a nanosecond, and then we have still 6 orders of magnitude down to the femtosecond regime. Yeah, so this is really short. Another way I like a lot to compare that is this scale. So here you can see the whole range from, in a way, 1 attosecond, 10 to the minus 18, to 1 second to 10 to the 18 attosecond, yeah, attoseconds. And if you calculate the age of the universe, this Big Bang was about 10 to the 18 seconds away. So from this you can say, okay, the ratio of 1 second in 1 attosecond, the ratio of 1 second into the age of the universe equals the ratio of 1 attosecond or a couple of 100 attoseconds or a femtosecond, so it's just a few orders of magnitude, to 1 second. Yeah, so if you're able to observe femto or 100 attoseconds, this is the same ratio as 1 second to the age of the universe. It's pretty impressive, I would say. What are the sorry, this should go away. What are the processes we can look at? So first of all, in the hundreds to 10 femtosecond regime, this is molecular movement. Yeah, so the time nuclei in molecules move is on the hundreds to 10 femtoseconds. For example, the CH stretch vibration has a period of 10 femtoseconds. Then in the few femtosecond regime, this is electron movement. Here you can see from a very nice science paper a couple of years ago, the electron, so this is calculations, of course, but the paper has measured these electron movements in a signal. And here you can, in a way, see that an electron goes back from here to here, back and forth across the molecule. So the movement of electrons is on the order of a few femtoseconds. And the shortest time resolution, attoseconds, around 10 attoseconds is the time it takes, for example, for an electron to be ionized out of an atom. Yeah, so you might ask, how long does it take if you photoionize an atom? How long does it take for the electron to come out? So again, electron movement. And more precisely, they ask, what is the time difference between ionizing a 1s electron and a 2p electron, for example, stuff like this. Yeah, and these are among the shortest processes that are observed nowadays, on the order of 10 attoseconds around. Okay.
Can I quickly ask about the pictures alongside with the millisecond and microsecond regime? I suppose that the eye is symbolizing the fact that the blink of an eye is about a second. But the others I don't quite get, just out of curiosity.
Yeah, sure. Thank you for asking. They're pretty small anyway. So second, meaning that, so a second is the time resolution you can resolve with your eye, basically. Yeah, we've seen a millisecond you can do with photography, conventional photography. Microsecond, this is flash lamp photography. So you take a photo, the shutter speed is probably milliseconds, but you use a light flash that illuminates the object you want to investigate only for a much shorter time. Yeah, so the time resolution is given by the light flash and not by the mechanical opening of the shutter. What is here is a billiard ball that's being shot through with a bullet. Okay, I don't like bullets so much, but this is one of the images that is being shown with this time resolution. And this is a microchip, so nanosecond resolution you can obtain with conventional electronics. I mean, if you probably if you try hard, if you do phase measurements and phase comparison measurements, you can with electronics get to 100 picoseconds or probably even 10 picoseconds. Yeah, but so very expensive. So 1 nanosecond corresponds to 1 gigahertz bandwidth. So if you can afford electronics going to 10 gigahertz or even 100 gigahertz bandwidth, which becomes quite expensive, then you can get to around 10 picoseconds or so with electronics, but that's it. Yeah, so here is definitely the limit where you can go with conventional electronic time measurement. Yeah, and beneath that you just need shorter events. Yeah, if you want to measure an event with, for example, 100 femtosecond time resolution, you need a shorter event. And what would you say is this event or this happening you can use there? I should have mentioned that, so thank you for the question again. So what's so short that you can, I mean, if you take a photo, if you use a photo camera to do time measurements, as we did in for these photographs of the cat, for example, the shutter speed must be much faster. Yeah, in order to have a time resolution, I did mention that this is about 10 milliseconds, I think, 100 milliseconds or so. So this was 10 photos per second, but the shutter opening time must yet be shorter than that. So you always have to have a shorter event in time in order to measure a slightly longer one. Yeah. So what allows you to break this limit and go beneath the picosecond regime? What do you use for time measurements there? Who has an idea?
Decay of atoms or something like that?
No, too slow. So if photoexcited, so the lifetime of potassium or alkyl metal atoms, the natural lifetime is tens of nanoseconds or a few nanoseconds. Probably radioactive decays would be faster or something like this, but no. What is the oscillation period of light? What's the frequency of light? So if you assume you have 800 nanometers, as function of time, the electric field is on the order of 10 to the 14 hertz. Yeah, so 10 to the 14 oscillations per second, and the period is 2.7 femtoseconds. Yeah, so in a way we do pretty much the same as flashlight photography, but we just make the shortest possible light pulses, and the shortest possible light pulse is around a single oscillation. Yeah, so for femtochemistry or femtosecond spectroscopy, you use, it's sufficient to have like 10, 20 femtoseconds time resolution. So we're talking about 4 to probably, or 5 to 10 oscillations of the light field. But so the shortest pulses we have in our lab at the moment is about 4 to 5 femtoseconds. So this is a single or probably 2 oscillations. Yeah. So again, this would be then a wave packet as function of time, electric field. If this is the envelope, a light pulse looks something like this. Very ugly drawing now. So this is kind of the shortest light flash you can produce, because you switch it on, the electric field does 1 to 2 oscillations and it's off again. Yeah. So same idea as for flashlight photography in a way, but with shorter light pulses. And then we also have this spectroscopic approach. So we investigate the interaction of these light pulses with the material we investigate. Okay.
But how do you get these short pulses switching on and off in the first place?
Yeah, very good questions. Wait 2 or 3 slides. There comes the answer. Okay. Before we go on though, motivation. I want to use one more slide on motivation. So the question is, why do you want to do this? If you want to have a laser lab, what do you think? How much costs such a laser system? How much do you have to spend in order to have a laser lab running, or the basic equipment to do these experiments? I have not, this kind of unfair, I know, because I have not told you how these lasers works, but anyway, if you would know, you wouldn't know the price anyway. So what's your guess? How much money do you have to invest?
800,000?
Around, yeah, that's a good guess. So about $1 million laser system, you can get such laser systems from 200,000 to 300,000 to, so one system we have is about 600,000. So you need some more equipment and good stabilization and stuff like this. So about 500,000 to $1 million is really the starting amount of money, the minimum amount of money you get. If you want to invest so much money, I think it's important to ask why. What is it good for? Okay, and this also allows me to talk about my motivation. Basically, what we do, we investigate light matter interaction. Yeah, we investigate how light interacts with materials, and it turns out that the processes that are induced after photoexcitation of more complex systems, not single atoms, but molecules or solid states, semiconductors, anything like that, the processes that take place are on the femto and picosecond time scale. Yeah, you have probably heard about the Born-Oppenheim approximation. They can separate electronic and nuclear degrees of freedom, and it turns out that in most cases, if you do a photoexcitation, almost all systems show non-Born-Oppenheimer very, very fast dynamics. So in order to be able to understand how light matter interaction really proceeds and what processes, primary processes take place there, you have to be able to investigate them. Okay, and again, you can ask, why do you want to investigate that? And the answer is, I can make, with this understanding, I can build something to use this light energy. Yeah, so you're all aware of this huge energy discussion, all the problems that are connected to usage of fossil fuels as primary energy source, like global warming, ocean acidification, and stuff like this. And this all would go away immediately if we would use solar energy, light energy coming from the sun. And there's plenty of that, really. I mean, there's about 1.4 kilowatts per square meter, not today, unfortunately, but in general, that the sun delivers to Earth. If you just learn to use this efficiently, there's no energy problem anymore. Yeah, and no environmental problem anymore. This is in part solved, I would say, with photovoltaics. Yeah, you can convert solar energy to electrical energy, but you know all these disadvantages. I cannot imagine that airplanes on a larger distance will work with batteries at the end. Yeah, so we must come up with another idea to convert the solar energy into other forms of energy, and this is clearly chemical energy. Yeah, and this is what this slide is about. So this is one research project I'm following. So photocatalytic water splitting, using the energy of the sun to split water. Yeah, and the basic idea is both is plenty. We have plenty of both. We have plenty of water on the planet, and there is sun coming. If we just can combine this and make out of water, so we start out with a water molecule. If we learn to make hydrogen gas efficiently, then the energy crisis would be solved. Now, of course, there are many approaches that do that, but unfortunately, none is so efficient and reliable, up to date, that it can be used on a commercial applications comparable to solar energy, as to photovoltaics. And what I'm following in this project is a suggestion of one of the a famous, very famous theoretical chemist, Professor Wolfgang Domke at TU Munich, and he has suggested a process some time ago, 5 years or so, a kind of new approach to this topic that has not been tested experimentally so far, and this is what we want to do in this project. So let me quickly walk you through this slide. So we're starting out with a molecule, pyridine. So this is in short PY. Pyridine, if you solve this in water, so this is the kind of photocatalyst. If you put this into water, there forms a hydrogen bond. So this red, this is a hydrogen bond, Wasserstoffbrückenbindung, and below case. And if you now photoexcite this complex, the pyridine, with one, or there are several water molecules, of course, around. If it's in, so there's a solvation shell around, there's just one hydrogen, one water molecule drawn. And so dissolve this pyridine water complex. If you photoexcite this, yeah, so this is the first photoexcitation process, then you trigger a charge transfer process. So an electron kind of goes over from the hydrogen, from the water to the pyridinium. So the water is missing one electron, and there's one electron at the pyridine. And as a second step, there follows a proton transfer. So this kind of breaking chemical bond breaks here, and the hydrogen follows to give a neutral pyridinium radical and an OH radical, which the two of which break apart. And next step is then, if we have the pyridinium radical, if we photoexcite that once more, this is a dissociative process, and so we split off one hydrogen atom and kind of receive our initial photocatalyst, the pyridine, and one hydrogen atom. And if you do the cycle 2 times, you can build a hydrogen molecule and collect this as a gas phase, in the gas phase. Yeah? So this has only been predicted in theory. This should work. Again, here we have some potential energy curves. This is kind of the field, the working field of quantum chemistry calculations. So we are looking again at the energy as a function of the, in this case, it's ROH. Yeah, let's zoom in here a little bit. So this is the distance of O and H in the water molecule. Yeah, so this is, if you wish, this is this distance here. So the distance from the distance of the one hydrogen that jumps over to the pyridinium to its oxygen nucleus. Yeah, and I really don't want to go into detail here, but we have photoexcitation. Then quantum chemistry says there's a conical intersection, electronic transition process, and another conical intersection, and the molecule goes back to the ground state here. Yeah. Anyway, the important point here is that these processes take place on the pico and femtosecond timescale and have to be therefore investigated with femtosecond spectroscopy. Yeah, so this is where we stand at the moment. We're setting up a system to investigate that. The main take-home message here is, however, and this is not only my personal motivation for that, but if you do spectroscopy, this is really, you're studying light matter interaction, and there's a huge application with the solar energy harvesting behind light matter interaction. Okay, so this is highly social relevant and meaningful application of spectroscopy, if you wish so. Okay, so we have, like, how much time do we have left? 15 minutes. This looks good. So now coming back to your question, how are these short pulses produced? Yeah, this is based on laser technology. So if you're really interested in that, I can only give you today a very quick overview. This is covered in great detail in ultrafast laser physics in the summer semester. So this is actually running at the moment, this lecture. If you want to take this, if you consider taking this lecture, please do fundamental optics before, because fundamental optics really gives the basis knowledge to understand ultrafast laser physics then. So we have to understand how laser works. You know that in part already. So we have a laser resonator, and you know there are different longitudinal modes in the laser resonator. Yeah? Different standing waves of different wavelengths. And typically, a free running laser, a CW laser, is emitting one wavelength at a time. Then it jumps to a different wavelength, so it jumps around a little bit and emits one longitudinal standing wave, and then another one, and back, and so on. Yeah. So this is connected to this important property of coherence length of a laser system. But if you are able to establish a phase relation between these longitudinal modes and have them running all at the same time, you're creating an optical wave packet. Yeah, this is very comparable to the particle wave packet, the de Broglie wavelength we just had before. This is just a superposition of several different longitudinal, very long harmonic waves, the longitudinal modes. And if the superposition contributes or consists of sufficient modes, you have constructive interference at one position and destructive interference everywhere else. Yeah, and because each of the different longitudinal modes has its own phase development, this wave packet moves kind of back and forth in the laser resonator. And whenever it comes to the output coupler, a semi-transparent mirror, it couples out a short laser pulse. Okay, the technique that achieves this mode coupling, this mode locking, is Kerr lens mode locking, so nonlinear optical effect, Kerr lens. And here I really have to well, I cannot go into detail here, but I really have to postpone this discussion to ultrafast laser physics. But in principle, you are coupling these longitudinal modes and generating out of these longitudinal modes a wave packet. So this is the solution how you produce these short light pulses. Is this, so the person who asked the question before, is this sufficient? Are you happy with this answer?
I'm happy with this answer. It was just general notion how it is established and the technicalities. I understand that this is definitely probably out of the range, but this is good enough for me to see where it comes from at least.
Okay, perfect. So same thing as for the laser cooling before. This is the fundamental process, how it's what the technical realization looks like, and there it becomes complicated. We do this in great detail. We'll talk through a femtosecond oscillator in fundamental optics. In ultrafast laser physics. Okay, so much about that. Let's look at these properties. Yeah, I've already mentioned, so the carrier wavelength often is 800 nanometers because these are titanium sapphire laser systems. These have been, well, up to now there's a second technique appearing on the market, but basically TiSAF is the working horse kind of the short laser pulse physics. Yeah, so this has a center wavelength of 800 nanometers, oscillation period of 2.7 femtoseconds, and if you do something like here, you would have a full half-width of about, I don't know, probably 6 to 8, well, yeah, or say 5 to 7 femtoseconds in this case, full half-width. Yeah. Now you know about energy time uncertainty principle. So that you can do a Fourier transformation. So this is covered by Fourier optics, also in fundamental optics. By Fourier optics, from the time to the frequency domain. So we can get from time to frequency domain by Fourier transformation. And if we do this, we see that Gaussian, so the envelope is typically a Gaussian distribution. The Fourier transformation of a Gaussian function is a Gauss function again. So we have a spectrum, and it turns out that for actually, yeah, so around probably 10 femtoseconds or so, you require a bandwidth of about 80 nanometers. Yeah, so there are about 10,000 longitudinal modes of the laser or so that are contained beneath the spectrum. I'm just indicating them here. But this is really kind of a continuous, a broadband spectrum of 80 nanometers, which is already about, well, the visible range is 400 to 800 nanometers. So this is a fifth of the visible range that you're able to see actually. So this is a huge bandwidth. Yeah. Oh, okay. I shouldn't be writing here. Unfortunately, I cannot erase this, so I apologize for this writing on that. So short pulses are connected to a broad spectrum. This is one thing you should remember, and short pulses are also very strong. Yeah. So here is so this is kind of a second characteristic property of these femtosecond laser pulses. So some numbers here are 25 femtosecond pulse. A pulse energy of 4 millijoule. This is a typical laser pulse energy we have in our lab. Is connected to a peak power. Yeah. So this is the electric field, but you know the electric field squared is proportional to the power. If you calculate the peak power, let's call it Tach or so. If you calculate the corresponding peak power, this is almost a terawatt. Yeah. So this is far more than the energy consumption of the city of Graz, I believe. So this is a huge power, but the point is it's on for just a very short time. So the duty cycle, it's off in our system for a millisecond and on for a few femtoseconds. So you have a duty cycle of about 10 to the 11 or so. So it's off for 10 to the 11, or it's on and then off for 10 to the 11 times as long. Yeah. Okay. If you, from this peak power, or if you directly measure the electric field strength here, the peak field strength, this depends on the focusing, the diameter of the laser beam, but sorry, typical values are 10 to the 10 or 10 to the 11 volts per meter. And this is comparable to the electric field an electron sees in an atom. Yeah, so we can drive very strong, highly nonlinear processes. And because, because these pulses, the field strength is so long, we are immediately entering the field of nonlinear optics. Unfortunately, my equations got messed up here. So there should be a polarization which is epsilon 0 times chi susceptibility, where chi is the linear susceptibility. And because the pulses are so strong, we have to talk about nonlinear optics. So we typically have to consider at least the second and the third order of depolarization. I don't want to go into detail here to save also some time. Again, if you're interested, this will all be covered in fundamental optics. The application we are using, for example, is second harmonic generation. So I'm sorry, this is all messed up. What it should be is, or should mean that if we have omega 0, so one laser frequency into a Chi2 active material, we get out omega, let's call this omega 1. We get out omega 1 and the double frequency, so 2 times omega 1. Okay, so just by shining this light into a any optical crystal, basically, allows you to do second harmonic generation. Yeah? And in the energy picture, you absorb 2 photons and re-emit a photon of twice the energy. Yeah, so you can do frequency conversation very, very efficient with the short laser pulses. So this is a fascinating field in terms of laser science. And what you can see here is a sketch of one of our devices we have, so-called optical parametric amplification or amplifier. So these are nonlinear processes that allow us to change the photon energy. So we're starting out, again, this is titanium sapphire, we're starting out at 800 nanometer. And this device allows us to change this energy, the photon energy, in a huge range from about, this is about 250 nanometer to about 1600 or so. Yeah, so by driving multiple nonlinear processes in sequence, we can change our photon energy. And this is important for spectroscopy, because if we want to investigate these nuclear-based molecules, for example, we just tune the OPA to, say, 260 nanometers, and you've seen in the spectra before that they absorb strongly there. So we can do a pump probe experiment, so a time-resolved experiment with this photoexcitation wavelengths of a nuclear-based molecule, if you wish. Okay. No. So, okay, now my notes again. Okay, so much about that. Pulse characterization, again, I want to speed up a little bit. The question is, how can you measure such short pulses? There's some mathematics. This is an autocorrelation technique. Basically, what you do is you build an interferometer. It's a Michelson interferometer typically, where you have your laser source, you split a beam splitter, and you split the thing in 2 pulses, or you split the single output pulse into 2 pulses, 1 and 2. And by moving one of the mirrors, you can change the delay between the 2 pulses. So you slide one pulse over the other and see how a nonlinear signal changes. So again, this is now the second harmonic generation. So we're using a nonlinear detection process there. And by measuring, I don't want to go into detail here, but by measuring the electric field, or we can measure the electric field or the interferometric autocorrelation, the intensity in the detector. And from this envelope, in a way, we can estimate the pulse duration. Yeah. So by doing, by comparing one pulse relative to the other, we make a single pulse, make a copy of it, we compare and shift the copy of the pulse with its original, and observing a nonlinear signal here. And by observing this nonlinear signal and the width, this tells us about the pulse duration. Okay, again, in the lecture, more detail. Yeah, sorry. So
can I ask just a quick question?
Sure.
The reason why you do not directly measure just one pulse is because you're not able to measure at this small time scale. Is that the reason?
Yeah. Okay, thank you very much for the question. I should have answered this right before. Again, the same thing applies. If you want to measure an event in time, you need another shorter event to compare it to. Yeah, if you stop the time of, I don't know, a racing car or whatever, skiing, for example. Yeah, if you measure the time, what you do is essentially a comparison to much shorter events in time, a stopwatch, for example. Yeah, here if the object to measure is around 20 femtosecond laser pulse, you need a shorter event in time in order to compare it to, and this you typically don't have. So the only thing you can do is you take the same event, a copy of the same event, and compare these two with respect to each other, and then with some mathematics, which is shown here, you can come up with a measurement of the duration. Okay.
Okay.
Is this?
Yeah. Thank you.
Yeah.
Yeah. And that can be done independent of the exact shape of the pulse. So you can, independent of the shape, you can tell about the length depending on the width of this pulse.
Yeah, at least a short.
So,
yeah, at least a short, a rough estimation. Yeah. The argumentation goes as follows: under the assumption that this pulse is Gaussian, we have a certain pulse. We can measure a certain pulse duration. If the envelope was not a Gauss but a sec square or whatever, any other shape, then the interpretation, the measurement would be wrong by a certain amount.
But you know that this is the case.
More or less. Well, this is where uncertainty treatment comes in. So you say you have a pulse duration of 25 plus minus 2 femtoseconds. So this is the range of uncertainty. And this covers for uncertainty of the shape of the envelope and things.
Okay. Yeah. Thank you.
And in addition, there are other techniques, much more complicated. This is a simple technique. There are much more complicated techniques that give different results, and by comparing that, you can get closer. But a very good question. Yeah, thank you. Okay, so how do you do an experiment? And this is the pump probe scheme. So again, as before, you use a beam splitter to split off, make a copy of the pulse, and the delayed pulse or the copy is guided across what we call a delay stage. So two mirrors that can be moved. Yeah, and by moving them, we can change the time delay between the two pulses. Yeah, and then we shoot the first pulse on the sample. This is just this gray cloud here, whatever, and with this defined delay, this the second pulse, and we see how this second pulse interacts with the system under investigation. And observe this. For example, to become a little bit more clear here, again, we have, so this, forget about this. This is just a reaction coordinate. We have a system in the ground state. We excite it with the first pulse to some excited state. The excited state would lead to an increase. So if this was, for example, again, this HO distance of these two atoms in the molecule, then after photoexcitation, the system would undergo relaxation, so the distance would increase. Yeah, and if so this is the pump pulse, and the probe pulse comes later, and we have drawn here 4 different pump probe time delays. So initial probing, 0 delay, delay 1, delay 2, and delay 3. And what the second pulse does, for example, and this is just one option, is photoionization. So it measures the photoelectron energy at this time of the, at a certain time, a well-defined time after pump excitation. If it's immediately, the distance from the excited to the ionic state is the lowest, and we get the highest photoelectron kinetic energy. Yeah. So if we do a measurement as function of delta T, this is the pump probe delay time, we if you plot the kinetic energy of the photoelectrons, we would measure at time, say this time 0 here, we would measure a rather high value. Then at time 2, we would measure a lower value. At time 3, yet a lower value, and I think you get the idea. So the photoelectron kinetic energy directly tells me about the distance in this case of the excited and the ionic state. So this provides me with insight into the system, how the the molecule evolves with time. Yeah, and typically this is a kind of an exponential decay, which has a characteristic decay time constant tau, which you can fit, and this tells me how the HO distance, how the hydrogen atom moves away from the oxygen atom in the molecule, for example. Yeah, but this is only one very specific time-resolved photoelectron spectroscopy. So this would be sorry, no, shoot. No, it's gone. This time-resolved photoelectron spectroscopy is just one very particular example. There are many, many different techniques and different observables how we can observe this process. Okay, so now I'm running out of time. Is it okay for you if I take 5 more minutes and give you one more example? Especially one example of my research, and then I will try to finish off. Do you agree?
For me, it's okay. Fine. I don't know what the others say.
Yes, for me it's okay.
This is a very, very particular example anyway. So whoever has to leave, I apologize for the delay. Yesterday when I went through the presentation, it was okay, but then with the questions it takes a little bit longer. So, but this is a very particular example. So you don't miss too much if you're not interested and just leave. Okay, so this is a second aspect of my research. So helium nanodroplet spectroscopy. So what we do, we use nanometer-sized helium nanodroplets or nanometer-sized helium droplets. This is a small droplet consisting of a few thousand to a few 10,000 helium atoms. This is superfluid, so in a way it's a quantum fluid, somewhat comparable to the Bose-Einstein condensate we had before, although at a somewhat higher temperature, 400 millikelvin, 0.4 Kelvin. So it's really a small droplet. And the thing is, you can put atoms and molecules inside and investigate them with spectroscopy. So this is a cold environment, a cold container for spectroscopy, and has been used so for 30 years now, roughly, but only for CW spectroscopy. And this is a very fascinating field, and this is one track of my research where I want to develop this helium droplet technique that is well established for CW spectroscopy into a tool for time-resolved femtosecond spectroscopy. Yeah, so you produce them in a droplet source by, or we produce them in a droplet source by a process that we call supersonic expansion. So just helium gas out of a nozzle. This is pre-cooled to 10 Kelvin. It cools down due to expansion. It cools down, forms these small droplets, and the small droplets just fly in a molecular beam approach. This is all under ultra-high vacuum through the machine. You can, we call it doping. We can dope them with different atoms and molecules just by establishing this vapor pressure, so a region where you have a vapor pressure, and then the atoms go, or molecules go into the droplet and are cooled down, and then they're investigated with this pump probe experiment. The lasers coming from the side, photoionizing it, and then we have a time of flight spectrometer, and we detect the flight time of the electrons and or ions, and learn about the dynamics. So the electrons you have seen on the previous slide, so the photoelectron kinetic energy can be measured as a flight time in this time of flight spectrometer. Okay. So what does this mean, or where does this lead to? So the first step was these helium droplets have been used for CW spectroscopy, but not really for time resolved. So one of the first steps we took 2 years ago was to dope a very simple system, a single atom, into the droplet and see how it behaves and reacts to photoexcitation. Yeah, so the simplest system, a single atom, indium atom in this case, and do the photoexcitation. And what you see here is in this is the time resolved photoelectron spectrogram. So the photoelectron kinetic energy as a function, oops, I forgot this, pump probe delay time, delta T. And you see that around time 0, you have rather high energies, and this energy decreases, yeah, from higher to lower values. And this can also be drawn in this one-dimensional plot here, which we have just discussed from before. So this tells me what the system does, and what it does is the following, that in a way this atom sits inside the helium droplet in a bubble, and if you photoexcite it, you know from atomic physics from your course, if you photoexcite an atom, the valence electron expands, and since the atom is sitting in a bubble up here, the bubble has to expand as well. So the radius of the valence electron expands, and the bubble has to adapt to that. This is the first thing. And the second step you can see in the movie here. So the second thing is the photoexcited atom is actually ejected out of the droplet. Yeah. So we also see this in the spectra in this by time resolved spectroscopy. Although these images here are from time-dependent density functional theory simulations. So we also do simulations to better understand our experiments. And in a way, in combination of these high-level simulations and the photoelectron spectroscopy with femtosecond resolution, we can investigate how these nanosystems behave. Yeah. If you're interested, you can go. We had a very nice Nature paper, Nature Communications, 2 years in 2018, October or so, about this. You can go and download it and read it. If you cannot find it, please write an email. I'm happy to send it to you. And also, like newspapers, like the Standard picked up on that. But the message I want to take here is, I mean, femtosecond spectroscopy has also been used for 30 years now or so to study these systems. And what I want to do is to use these helium droplets and kind of generate or investigate systems that cannot be investigated with other techniques. And here we are taking the first steps. Okay, so much about this. Here would be a couple of slides for photoelectron, photoion detection. I will skip that in terms of time and just give you, and this is my last slide. I would like to conclude with an overview what processes can take place actually if you photoexcite a molecule with a short pulse. And these are very many. So you can excite different vibrational excited states. So you form a vibrational wave packet, and there it is again. So you see, wave packets are important for laser physics to understand the short pulses, but also the vibration of a molecule. So the very same concept. Once you have understood the concept of a wave packet, you can apply this to different regimes. What else can take place? The excited state can undergo relaxation to lower states. The molecule can break apart if you put too much energy into it above the dissociation limit, so it just dissociates. You can ionize it. Actually, what you do as a probing step, so you just shoot off an electron from the atom or the molecule. The most boring thing is luminescence. So if no ultra-fast processes take place, after about a nanosecond or so, or 1 to 10 nanoseconds, it will relax to the lower state and emit a photon by spontaneous emission. Yeah, electronic relaxation, as we also had before, quickly. So it might encounter crossing of different electronic states and go to different electronic state. This is important for charge transfer processes also. Isomerization, it can change its shape. So the overall shape of a macromolecule can change, or charge transfer. So So this is just what we had before on the pyridine molecule. So in principle, we can study how energy and charges flow in a molecule after photoexcitation. And with this understanding, we can learn how to convert this photoexcitation energy into other energy forms. Okay, so with this, I'm at the end. I want to close with one more funny picture. So the take-home message probably for you is, I hope I could convince you at least that just observing the initial state of a system and the final state is just boring, and all the fun actually really lies in observing how the system comes as a function of time from the initial to the final state. So, okay, so this would be it from my side. Do you have questions? So I'm still open for discussion and questions as long as you wish.
Yes, I have a question. You said that you look at a photoexcitation of a particle or of an atom, but
yes,
when you detect the laser, then somewhere you have to have a detector, and in the detector you do as well a photoexcitation of something.
mm-hmm.
So this takes the same time as your initial the initial thing you were observing. So
mm-hmm.
how does this work when these both are the same time span?
Yeah, very good question. Thank you. Let me go back to this pump probe concept. One more. There we go. The thing is, the detection, so the observation, whatever it is, be it photons, be it electrons or nuclear, this is not time resolved. This can take place on a much longer time scale. What we measure is how the system, so we have the two pulses, the pump pulse and the probe pulse, and we increase the time delay between the two, and we see how the action of the probe pulse, how this changes as a function of the pump probe time delay. Yeah. So for example, in photoelectron spectroscopy, I do a pump excitation, and for example, say 50 femtoseconds later, I do probe ionization. Yeah. And then the detection of the kinetic energy is dependent on the development of the system, the molecule, within these 50 femtoseconds. But the detection of the electron can take a microsecond or longer, and it does actually. Yeah. So the time resolution is only given by the time delay between the pump and the probe. If I increase this to 100 femtoseconds, the photoelectron kinetic energy has changed because the molecule had more time to evolve, to develop. But again, the detection of the photoelectron can take a microsecond.
So only the differences between the detections are interesting, and not how long it takes to detect a certain state.
Exactly. Yeah, exactly.
Okay.
So no detector exists with femtosecond time resolution. Yeah. But it's only this is why this pump probe concept is so important, because we only observe how the system evolves between the pump and the probe pulse, and then in a way after the probe pulse the experiment is over, and then detection of the photons or electrons, ions, whatever, is afterwards and not important. This is a general concept. Now you can discuss again long time. There are exceptions to that, but in principle this is the general concept.
Okay, thank you.
You're welcome. More questions, please.
Yes, maybe something that can be easily answered. Maybe I just missed it, or depends on the. Where did we get that these pulses have a high energy, a high peak energy? So how did we conclude this from just the short pulses?
Yeah, probably was a bit quick there. The thing is, if I draw as a function of time the output pulses, so these are the pulses that come out of my laser system. Yeah, each of the pulses has a duration of say 20 femtosecond or say 100 femtoseconds, so it's easier. And the delay between this is a millisecond. Yeah. So this is roughly a ratio. Let me think. 10 to the 7. Is this a kilohertz? Micron nano pico? No, 10 to the 11. This is a ratio of 10 to the 11. Yeah. So this is you can call this a duty cycle. If this was a voltage, this is a duty cycle on divided by off time. So this is the laser is off for 10 to the 11 times the on time. Yeah, the time average, the average power is in this case 10 watts. Say, yeah, our laser system has about 13 watts or so, so roughly 10 watts. Yeah, so this is just the time average. If I measure with a slow detector, then it's well, the power. It's 10 watts in on time average. So this is a nonlinear scale now. So the peak power is actually 10 to the 12 watt. Then, okay. This is just because it's a pretty strong laser by itself. 10 watt is pretty intense. But on top of that, it's for a CW laser, this would be a strong laser system, but since it's a pulsed laser femtosecond system, it's off for almost all the time and then on for just a very short amount of time, and then it's insanely strong, basically. Yeah. Does this answer the question?
Yeah, it answers the question. It's just we have a certain given power in that sense, but we have to condense it to short times.
Yeah,
and
exactly.
else it's just nothing. Okay.
Yeah,
no?
pretty similar actually. Yeah, pretty simple. Sorry, pretty simple. More questions, please.
But do we need such a high pulse, or is it just from the techniques that it comes?
Depends on which experiment you want to do. Kind of the research divides here into regimes. You have the kind of spectroscopy regime where you, or the linear regime, okay? If we do experiments, for example, let me go back to this example here. So this is a linear regime because we do a one photon excitation and a one photon probe, yeah? On the other side, there are strong field experiments which do exactly the opposite. Now I have to draw. We just go back to the values. So this would be the linear regime experiment and spectroscopy. This is femtosecond time resolved spectroscopy, if you wish. The strong field regime, is something else. So if you have, probably for an atom, the energy as a function of distance, yeah. You have this Coulomb potential. Oh, nicely here. So this is the Coulomb potential binding the electron. You have some core electrons, you have a valence electron, and then you have unpopulated free valence-excited states. Yeah. And the ionization potential, for example, if this would be xenon, so rare gas atoms, for example, this is about, the ionization energy is about 12.6, I believe, electron volts. So you can ionize this with a single photon of at least 12.6 eV, or you can do a multi-photon ionization. So the 800 nanometers have a photon energy of about 1.55 eV. Yeah. So you need, I don't know, 8 of these photons to, so the drawing is not to scale now, to ionize it. And even after ionization, you can further excite the electron, and the electron comes out with increased energy. So this is a strong field multiphoton ionization. So because the laser is so strong, you have a pretty high probability that you do this 7 or 8 photon excitation and ionization of the system with a single pulse. So this goes into the strong field regime, which is a research field by itself. So to answer your question, so depending on the application, for some applications it's more the wavelengths and not so strong fields actually. And for other experiments, they focus very hard and try to get as high fields as possible and drive these nonlinear strong field effects.
Okay, thank you.
Please, more questions. I'm happy about the discussion because I believe this is all pretty new, or I hope this is all pretty new to you. So, and we had a very dense kind of lecture, so a lot of new information, I believe. And still, it's good that you have so many questions because it shows that you have gained something out of it and actually understood what it was about. Okay, are there further more questions?
Yes, I have a question, but not about the lecture.
Mhm.
Also ich würde gerne meine Masterarbeit mit Ultrafast Lasers machen.
Ja.
Und ich habe ja schon die ganzen Vorlesungen gemacht von beiden Optikzweigen und habe da mal den Probetag vorgeschlagen bekommen. Ich würde den ganz gern machen.
Ah, ja, sehr gern. Georg, richtig?
Na, Raphael.
Ah, Raphael, richtig? Entschuldigung, sagst du mir den Namen nochmal? Ich habe jetzt gerade...
Raphael Dorner.
Ah, Raphael, genau. Schreib mir bitte E-Mail und wir machen da was aus. Ja?
Ja.
Also das ist auch für die anderen, die sich dafür interessieren. Ich biete immer so einen Probetag, einen Schnuppertag an. Also wer dafür interessiert, ich würde auf jeden Fall empfehlen, die Fundamental Optics und die Ultrafast Laser Physics zu besuchen. Da kriegt es mehr Einblick. Aber dann, wenn es euch dafür interessiert, dann gibt es die Möglichkeit, dass wir so einen Probeschnuppertag machen. Ihr kommt einmal vorbei auf einen halben Tag, arbeitet mit, dann seht, was so wirklich die tägliche Tätigkeit im Labor ist. Das ist ganz was anderes, als man da in den Präsentationen sieht. Und dann können wir uns unterhalten darüber, ob eine Masterarbeit oder so passen könnte.
Okay, dann schreibe ich mir.
Ja, super. Gut.
Danke.
Ja. Hat noch wer eine Frage? Gut, falls euch irgendwas noch auf der Zunge liegt oder später einfällt, einfach eine E-Mail schreiben. Ich habe die Vorlesung aufzeichnet, ich werde es auch hochladen oder werde den Andi Hauser bitten, dass er das hochladet. Das heißt, man kann dann das offline im Nachhinein anschauen. Und falls eine Frage aufkommt oder irgendeine Information, wollt einfach eine E-Mail schreiben, bitte. Alles klar, dann wünsche ich noch einen schönen Tag und gutes Gelingen mit der Vorlesung weiterhin.
Danke sehr.
Sehr, sehr.
Schönen Nachmittag.